We've been playing a lot with the mean value theorem lately, and in the last video, I showed you this kind of extended form of the mean value theorem. And again, this can look a little gross and intimidating, but really what we said in the last video is that if we were to make an analogy to speed, that we're saying that all this is saying is, okay, the average speed is in between the minimum and the maximum speed. And we go, oh, duh, we know that. And I want to apply this kind of extended form of the mean value theorem to solve a cool new type of problem. So here's the problem. Suppose we were to give you a derivative function, 4x squared plus 2x plus 1, and we were to tell you what f of 0 is, that it's 7. Now, what could you conclude from the mean value theorem? You could conclude from the mean value theorem that our function, our original function evaluated at 1, is going to be in between some a and b value. And we want to find what those a and b values are. So why don't you pause the video and use this extended form of the mean value theorem in order to find what these uppercase a and b values are. All right. Assuming that you've given it a go. Again, I think a good place to start is kind of looking at the mean value theorem as we know it, this how you were first introduced to it. And we're just going to try to figure out, okay, how could we write out kind of some information that we see in this problem statement here and start to write out the mean value theorem. And we need to figure out, okay, what is lowercase b and lowercase a here? And I think two good candidates would be f of 1 and f of 0. That's kind of the only candidates we have in this problem statement. So let's just write out and see what that would look like. So I'm going to let lowercase b be equal to 1 and lowercase a be equal to 0. And now writing out the mean value theorem, we find this. So we have f of 1 minus f of 0. And then we have over 1 minus 0 is equal to f prime of c, and now c is in between 0 and 1. C is between 0 and 1. Okay, and now we're just going to toss down these two ends here. So we have this here, our minimum derivative value, and again, x is going to be between 0 and 1, including both 0 and 1, and then our maximum derivative value, And again, x is going to be between 0 and 1, including 0 and 1. So this is what we have, kind of trying to write out what we could take out of this problem statement here. And we have a few extra things to fill in. I mean, we already know what f of 0 is. We're told that's 7. But then we need to figure out, okay, what is the minimum and maximum derivative values on this closed interval? So we need to find that out. And just one quick thing here. When you work on problems like this, one thing to notice, we have a 1 in this denominator. So it's not really doing anything for us here. We don't have to really get rid of it at all or do anything with it. But just say, okay, let's say instead of f of 1, we had f of 4 here. We had f of 4. So we'd have 4 minus 0 in this denominator, and we would have to get rid of it. And one thing that I've made in the past, an error trying to go pretty fast here, is that I did not multiply that 4, if we were to continue the example that we're hypothetically talking about, that I would only multiply it to f prime of c. But you can't do that. You have to multiply it to every part of this inequality here. So don't make the same mistakes that I have made before. And remember to, whenever you're getting rid of a denominator, to multiply it to every side of the inequality. So just a quick reminder there. Now, we want to, again, let's fill in what f of 0 is. So we'll just write this guy out. We have f of 1 minus 7. And this is going to be equal to f prime of c. And again, we'll just drop down what we've already said. So we want to figure out now what the minimum and maximum derivative values are. And thank goodness they gave us the derivative function. So let's write out our derivative function and start playing with it a little bit. So we have a 4x squared plus 2x plus 1. Okay, and you know what? You could look at this analytically, and we probably will, but I think always a good thing to do is to try to graph something just to get a feel for what it looks like. So we could try to graph this. Maybe we can complete the square. So we have f prime of x. Let's factor out a 4. we have x squared plus 1/2 x, and then plus 1/4 over here. 1/2 of 1/2 is going to be 1/4. 1/4 squared, 1/16. So minus 1/16 as well. And then completing the square, we have 4 times x, not squared, not yet, plus 1/4. This whole quantity gets squared. And then 1/4 minus 1/16 is 3/16. And then times 4 is 12/16. So that's 3/4. So we just completed the square. And now we can get a nice graph for this. So let's see what this guy looks like. And again, just a rough sketch. Oh, maybe we'll grab some other space. We'll put it more over here like that. Okay. So negative 1/4. Okay. And maybe this could be 3/4. And then we'd get a upward facing parabola. And again, we're just trying to get a sketch here. We're just trying to get the shape of this graph going. So here's what we have here. Something like that. Okay. And we'll let 1 be over here. And we're interested in the interval from 0 to 1. We're interested in this interval from 0 to 1. And again, this is a very rough sketch. Very rough sketch. But again, what are we after? Well, we ultimately want to find the minimum and maximum values. And again, this is the graph of the derivative function. Okay, this is the graph of the derivative function. So we just need to find the minimum and maximum values. And graphically, you can see that they're going to occur at the endpoints. That our minimum value for our derivative function is going to be at when f prime of 0, and our maximum value is going to be f prime of 1. You can see that, and we could even verify this analytically. So we could take the derivative of the derivative, which would be the second derivative, and we would get, let's see here, 8x plus 2. So we have 8x plus 2, and you can see on our interval from 0 to 1, including both of those endpoints here, our second derivative is going to be positive on this interval. And therefore, f prime is going to be increasing over this whole interval, and therefore our minimum value and maximum values are going to occur at our endpoints. Because, again, minimum and maximum values for functions on a fixed interval, on a closed interval, can only occur at a critical point or at the endpoints. And we don't have any critical points on our interval, so they're going to be at the endpoints. So we can feel pretty good about those. Now, one subtle thing I want to say. Let's actually stay up here. One subtle thing I want to say. Maybe you've noticed. Again, we're saying that in our problem statement, A is strictly less than f of 1, which is strictly less than b. But down here, we do not have strict inequalities. So how do we reconcile those things? Well, one thing to note with this particular function here, this particular derivative function, what you can note is since we have our minimum and maximum values occurring at our endpoints, where can C range? C can range between 0 and 1, but it's not including 0 or 1. So it's not including our endpoints. And therefore, we can say that these can be strict inequalities. So therefore, we could write this. We could write that f prime of 0 is strictly going to be less than f of 1 minus 7, which is strictly less than f prime of 1. And again, that is because these 2 values here occur at the endpoints, and C cannot take on the endpoints. Now, again, I'll just give you another example here. If you were to have another type of problem that looks like this, and you were to look at a function over a closed interval, and maybe it looked something like this, all right? And you're looking at this interval here. Well, then you couldn't have strict inequalities because these minimum and maximum values occur in between the endpoints. So you would have to have these less strict inequalities up here. But again, because our minimum and maximum derivative values occur at our endpoints for this closed interval, well, then we are able to put on these strict inequalities. So I hope you feel good about that. Now, again, we're almost done. We just need to find what f prime of 0 is, f prime of 1. So let's quick do that. So our derivative function evaluated at 1 is going to be 4 plus 2 plus 1. That is 7. So we have 7, and this is f of 1 minus 7. And what is f prime of 0? f prime of 0 is going to be 1, 1. And now all we need to do is add 7 to both sides. So we have 8. We have f of 1 is going to be greater than 8 and less than 14. So that is our answer. That is our answer, which is pretty cool. And again, we use the mean value theorem to do that. We are only given the derivative function. We're able to analyze our derivative function's graph and fill in this extended form of the mean value theorem to get these bounds. And one last thing before you go. This is going to be coming up shortly, if you don't already know this. So this right here is called an integral. And we're actually going, since we have our derivative function, we are actually going to anti-differentiate real quick. I just really want you to feel good that these bounds that we found are legit. So what is our derivative function? Our derivative function is 4x squared plus 2x plus 1. So this is 4x squared plus 2x plus 1. And again, you don't need to know how to do this yet, but you'll see this very soon. What we're going to do, because this is our derivative function, we're going to anti-differentiate. So we're going to get our original function out. So we get 4/3 x cubed plus x squared plus x and then plus c. And that is our original function. And now if we were to evaluate this original function at 0, well, we were told that f of 0 is 7. So this c value is 7. So now, again, if I were to write this out, f of x is equal to 4/3 times x cubed plus x squared plus x plus 7. And again, we want to know what f of 1 is. So f of 1 is going to be 4/3 plus 1 plus 1 plus 7. So that's 9 plus 4/3. So that's 10. That's 10 and 1/3, which you can see is definitely in between 8 and 14. So you can feel good about these bounds that we found.